Good morning, everyone. My name is Shashank, and I'm a second-year graduate student in Professor Moini's lab at Princeton University. And today, I'm going to talk about the microstructural heterogeneities, fracture, and transport in layered 3D printed cementitious materials. So, the presence of the interfacial zone in 3D printed material is a well-established fact in the 3D printing community. We have talked about it in the various presentations today. This interfacial zone stems from the lubrication layer during the extrusion process, where lubrication layer is just a water-rich region due to the shear induced motion of the particles during the fabrication process. Now this brings us to the question, what does the microstructure of the interfacial zone looks like, and how does this interfacial zone affects the mechanical properties of the 3D printed material? Coming from those two questions, the three objectives of the studies are to understand the interfacial heterogeneities in the fracture response and cracking mechanism in the two orthogonal direction of the 3D printed sample, and to understand the microstructure phases at the core and the interfacial zone using the scanning electron microscopy and micro-CT. And finally, we will be understanding the transport phenomena and effect of those microstructural heterogeneities using neutron radiography. So I think we have been already talking about this process of fabrication in our previous presentation. So the setup was being defined. So first thing was that we did was to define the input geometrical parameters of these architecture, and we created these contours. The contour is just a path, a curve that the print head will follow. And then this contour was deconstructed in point that was taken into the G code. The 3D printed sample is at the bottom. It is with a water cement ratio of 0.275, and we added admixtures, high range water reducing admixtures, and the viscosity modifying agents for the flowability of the material. Now, let's start with the first objective. Let's understand the role of interfacial heterogeneities on fracture response. I will start with a bit of a background on the fracture characterization. The cast material are assembled to have uniformly distributed heterogeneities. However, when we move to the 3D printed material, things are a bit different because we have a layered heterogeneities. Now, the traditional methods that we have been using, it's created certain issues. For example, 3D printed material, the fracture is sensitive to the location of the notch in the material. And the second issue is it's also sensitive to the orientation to the applied load. So this brings us to two questions. How do you locate these notches in the precise location? And how do we determine fracture sensitivity to the interface orientation? Now let's try to question those answered by certain propositions that we have made. So we have used laser processing to create notches as a precise location in 3D printed material. They are quite accurate. We have also seen that they create sharp notches, and we have tunable laser processing parameters to engineer the depth of the material. I will talk a bit more about it. So the effect of the laser parameters can be seen versus the speed and the power in this plot in there. As you can see, as we increase the power, we can actually tune the depth of the notch. The same thing can be done with the reducing the speed of the laser. With the 30-watt laser setup, we were able to get the depth of 3 millimeter in these cementitious material. The microscopic pictures of the two views also shows that the notch was quite sharp. So yeah, that was the sort of a problem that we tried to solve. The first question that I proposed. The second thing that we have done is to take the Brazil nut test to study the sensitivity of fracture to interfaces. So what is Brazil nut test? It is we have a cylindrical specimen with a central notch that goes through the entire depth of the sample. One of the advantages of this test is that with the same testing setup and the sample, we can test either the fracture mode 1 fracture toughness or mode 2 fracture toughness as the function of the diametral compression angle theta. As you can see the plot, at theta is equal to 0 degree, the mode 1 the fracture toughness was in mode 1 at the crack tip, and at 26 degree it is the crack tip is entirely in the mode 2. Now, everything in his life has positive and negative. So the negatives that we have got in this particular experiment was the partial notches were obtained at 30 watt power. That was one of the challenge. The second, so how did we sort it? It was the modification of the analytical equation that has been developed to do those tests. Let's talk a bit more about that. So as you can see, we obtained two partial notches at the front and the back of the sample. There was a small region between these two partial notches that will require additional fracture energy. So to account for that, we have proposed the effective depth of the sample. Um, and we have verified the new analytical equation by comparing it to the already existing literature of the same cement composition, and also comparing the result with the single edge bending, notch bending results. I also want to bring your focus into how do we notch these samples, where was the notch tips located, as I've already mentioned, as I've already focused on that point. So the notch tips were positioned in two positions, in two directions, interfaces in the parallel direction, and in the perpendicular direction, the notch tip was on the filament. So what did we get at the end? What was the results? So in the parallel direction and in perpendicular direction in mode 1, the fracture toughness was significant statistically similar to the cast. However, when we moved to mode 2, we saw a significant increase in the fracture toughness in perpendicular direction. Now that was interesting. Why did it happen? We thought about it, and to answer that, we looked at the crack propagation in the sample. So in mode 1, perpendicular and parallel, we saw planar crack propagation from the notches. However, when we moved to mode 2, there was in-plane crack deflection and out-of-plane crack deflection was observed in the parallel and perpendicular. So what we hypothesize is that presence of the weak porous interfaces in the interfacial zone leads to mixed mode loading in the perpendicular direction, which may have significantly increased the fracture toughness in the perpendicular sample in mode 2. This leads us to understand the microstructure phases at the core filament and interfacial region. So we performed the scanning electron microscopy, and from those two, we saw we characterized the interfacial zone in the perpendicular and the parallel direction. The porosity in the parallel direction was higher in the interfacial zone than in filament by 7.2%. At the same time, we observed that the hydrated cement was 8.5% lower in the interfacial zone as compared to the core of filament. We also observed the microchannels that constituted around 2.5% porosity of the total porosity in these 3D printed samples. Furthermore, we also inspected these samples in the micro-CT, and we observed that the interfacial regions was not only heterogeneous, these heterogeneities were not uniform. As you can see from the parallel direction, the microchannels were not uniformly presented over all the cross-section of the samples, and they were also non-uniformly distributed. Now, we didn't stop here. We wanted to understand the effect of these heterogeneities on transport as well. So the transport study was done by our collaborators at Oregon State University. We have designed these samples, and they have inspected the water absorption in two perpendicular directions. So what we have observed that in parallel direction, there was a higher water absorption. Now, our initial hypothesis was that these microstructure heterogeneities in parallel direction, the interfacial zone, they are actually causing the higher water absorption. However, we were proven wrong. From the capillary pressure versus pore radius, you can see that the capillary pressure decreases as we increases the pore radius. That's therefore the interfacial zone that have larger size of the pores have lower capillary pressure and have lower transport phenomena. So these interfacial zones actually act as a capillary brake rather than supporting the transport phenomena in the 3D printed sample. So in conclusion, we propose a novel approach to use laser processing for notching cementitious material. We also observe that the interface can be harnessed to improve the shear resistance in 3D printed material by engineering crack toughening mechanism, for example, crack deflection. And the third conclusion was the pore size and heterogeneities in the interfaces, and filament can control the directionality of the water transport. We would like to acknowledge NSF-ECI for the support, and also the Image Analysis Center, CEAS, and the Organ Trigger Reactor. The work has already been accepted for publication. You can look more into that in the paper. And if you want to know more about the laser processing of these concrete or cementitious material, there's another work that we have been working on, and it's been published. So